Let's calculate some cross products. I'm hoping that you remember some of the things that we have to do with matrices, because the cross product has a lot to do with matrices. Specifically, the easiest way to write out the cross product is to say that the cross product is each of the unit vectors in one row compared to the components of V and the components of W, and then take the determinant of that matrix. So, you'll notice that here is what we see placed before I, the unit vector I. Here is what we see placed before the unit vector J. And here is what we see placed before the unit vector K. So this is from the idea that to find the determinant, you're looking at each piece in one row or column, and then crossing out all of the pieces. Crossing out all of the pieces that share a column and row with it, and multiplying by that. There is one big piece of this that people miss, which is that negative sign. Please be aware of the negative sign between the unit vector in I's direction and the unit vector in J's direction. It's important that it's negative, this determinant times J. If you've forgotten how to take the determinant of a two-dimensional matrix, A, B, C, D, this is your friendly reminder that is AD minus BC, and we're going to be using that for each of the two-dimensional matrices. If you've forgotten determinants, now is a good time to review them. So, let's write this out. We have I hat, J hat, K hat, and then we'll write out them in order. The order does matter. If you put them in the opposite order, you'll get the opposite answer. So this is the correct setup. And then when we write this out, we're going to want to write I hat with the other columns and rows. That's negative 3, 4, 3, and 3. Then for J hat, make sure that you have the negative sign there. And then we'll look at 4, 4, negative 7, 3. So that's 4, 4, negative 7, and 3, J hat. Plus, and for K, we'll cross out this column, this row, and we get 4, negative 3, 7, negative 7, 3, K hat. Yes. All right, so it's worth double checking that there weren't any mistakes. I don't believe there were. Now we have to use the two-dimensional determinant. So this is going to be negative 3 times 3 is negative 9, minus 4 times 3 is 12. Here we have 4 times 3 is 12, minus negative 7 times 4 is negative 28. Here we have 4 times 3 is 12, minus negative 7 times negative 3 is 21. We then combine these, we get negative 21 I hat, minus, this would be 40 J hat, and this is negative 9 K hat. So this is the vector that is the cross product of these. Typically, if the original one is written in component form, we'll rewrite the result in component form. Negative 21, negative 40, negative 9. Calculate the cross product of these two. So, IJK, we have 1, negative 5. It's okay to just write the coefficients. All right, so let's begin. We're going to start with listing out these. This has addition, this has subtraction. For I hat, we're going to use this bottom right matrix. For j hat, we'll use 1, 6, -4, and 8. These aren't choices. You have to use those. 1, -5, -4, and 5. So please make sure that you see how these are matching up with the parts of the original matrix. Now, we're doing the two-dimensional 40, -40, minus 30. Here we have 8 minus -24. 8 minus -24. And 5 minus +20. So this is -70 I hat. This is 32, so minus 32 j hat, and minus 15 k hat. So that's the second cross product. A third cross product. So I, j, k. -7, -9, 8. It always has to be the first vector first. Now, I prefer just writing these out first, just to remind myself of the structure. Now, I hat is the bottom right vector. K hat is the bottom left matrix, excuse me, not vector. And then j hat uses this and that. The first row, the first column and the last column. So, -9 times 5, 7 times 8, with subtraction between them. -7 times 5, +7 times 8, with subtraction between them. -7 times 7, 7 times -9, with subtraction between them. So now this becomes -101. Oh, I lost the j hat. These add up to what? 91, and then -91, and then there's a negative in front, so it becomes +91 j hat. And this is +63. So +63 minus 49 is +14. So +14 k hat. That is the cross product. There is one type of problem that we're going to deal with cross products that it's not directly stated that we're looking for the cross product, but the area of a parallelogram formed from adjacent vectors is done with the cross product as well. You'll notice that these don't have z components, but you can still do it with placing the z component as 0. Sometimes you'll have two vectors that are in 3 dimensions, and then you can just do it normally as well. So the area of a parallelogram formed can be described by the cross product. 8, 6, 0, -2, -4, 0. Now it's worth mentioning that there is a possibility that we get a negative value here, and then we just take the absolute value at the end if we're talking about area. Cross products, we don't always do that, but this might give us a negative value. Essentially, it's the magnitude of this value will give us the area. So this is the same thing as what we're doing is we're taking the cross product of 8, 6, 0, and -2, -4, 0. So this becomes, place out our unit vectors, the signs, and the determinants Now let's fill in the matrices. 6, 0, negative 4, 0. 8, 0, negative 2, 0. And 8, 6, negative 2, negative 4. Now you might immediately notice what's going to happen with these first two, that they're going to become 0, but let me just do it out to show you that it's going to become 0. We have 6 times 0, which is 0, minus 0 times negative 4, which is 0. Here we have 8 times 0, which is 0. We have negative 2 times 0, which is 0. And here, we have 8 times negative 4, which is negative 32. Here we have negative 2 times 6, which is negative 12. We put subtraction between them. So we have 0 plus 0 plus, this becomes negative 20 k hat. So the cross product is negative 20 k hat, and then the magnitude of that will give us the area. So the area between of that parallelogram is 20. So that's one of the things that cross products can be used for, the area of a parallelogram.